Okay, so we've talked about voltage or potential difference, and that's what makes the electrons move. Then we talked about current, which is how fast the electrons are moving in amps. Now we're going to talk about resistance. Okay, resistance, it does what it says it's going to do. It resists the flow of electrons. Why would we want resistance when we just made a potential difference, voltage, so that we can get the current to start to flow? Why would we want to slow that down? Well, one, if the current gets to be too high, it gets to be hot and it could cause a fire or it could cause wires to melt. Okay? Two, we want to use that resistance to do something. In a light bulb, that resistance goes into creating light, so that energy gets transferred from the electrons into producing some light. If it's a stereo, some of that energy goes into making sound. Okay? So we're taking energy from the electrons when we slow them down and doing things with it. Okay? So that's why we want to have some resistance. Resistance is, we use a symbol R to represent it. The units are ohms. Okay? And we don't use the letter O for the symbol because if we did, and we tried to write the number like 15 ohms, it might look like 150, okay? So instead we use the Greek letter O, so omega, and it's the capital omega. The equation, voltage is equal to current times resistance. This is Ohm's law. And then we're going to talk about a couple things. We've got ohmic material and non-ohmic material. Ohmic material has a constant resistance over a range of currents. So it doesn't matter what the current is, the resistance is the same. And when we're doing problems, we want to have ohmic materials. So unless told otherwise, we're going to assume that the problems that we get when we're given a resistance, it's for an ohmic material. But there are things that are not ohmic. Okay? They have a variable resistance over a range of currents. For example, a diode. A diode allows the current to flow one way very easily, but it will not allow the current to flow in the opposite direction. So what affects the resistance of a wire? Because we were talking about resistance and we said, you could have the light bulb, you could have a stereo, we're taking that, we're doing something with it. But unfortunately, those aren't the only parts of our circuit that have resistance. Wire also has resistance. What affects the resistance of the wire are these things. The first one is length. Okay? Imagine you have to go from the science department all the way down into the basement. Okay? You have got a lot of ground to cover. And you're going to encounter more resistance along the way because you have a lot of ground to cover versus if you were just going from your chem class just a few doors down the hall to the art rooms. Okay? You wouldn't encounter as much resistance. Okay? The second one is the cross-sectional area or the width. Okay? So here, the longer, the more resistance we are. Cross-sectional area or width, well, think about the similar analogy here. If you're in the hallway and we've got a really small or narrow hallway and you've got all these people in it, it's going to be a lot of resistance. You can't get around people as easily. Whereas if there's a nice big wide hallway, okay, you're going to be able to maneuver your way around and pass people and move around a little bit better. So for cross-sectional area, the narrower it is, the more resistance that you will encounter. The third thing is simply the type of material. Okay? Metals are good conductors. They have less resistance than an insulator. Okay? Think about just the type of material. Say that now we're going to be driving, okay? So let's go ahead and you are driving along. You're driving on a nice paved road. You're not having a whole lot of resistance. The material plays a part in that. Versus if you're on a gravel or a dirt road, okay, and there's a lot more resistance there because of the material. Okay, so it's length, cross-sectional area, material, and then temperature. Well, why would temperature play a part? Go back to the thermodynamics unit. We talked about entropy. Okay? When things were hotter, there was more entropy. Okay? That means there's more things that you have to avoid, more things that are all out of place. Okay? And you've got to try to avoid all those things. Versus when we make it colder, things get a little more organized, and you can kind of predict where they're going to be, and so you can avoid them easily. Okay, so for temperature, the lower the temperature, the less resistance. The higher the temperature, the more resistance. This is where we're going to lead into superconductor. Okay? A superconductor has zero resistance at or below a certain temperature. And we've got some made of various materials, okay? And the temperature right now is extremely cold, okay? But what happens in a superconductor is that the current continues even after the voltage is removed. Now this could be very important for us. Why? Because if it has zero resistance at or below the certain temperature, then if we can make a superconductor that has zero resistance at the outside temperature where all the wires are connecting the electricity to our houses, then we're not going to lose any of that electricity, any of that energy to heating up the wire, okay? It's not going to be lost there. So what we're trying to do right now is make a material that is a superconductor at temperatures that are the average outside temperatures.